Hello. In this problem, we're going to be talking about how to calculate a value at risk at the 95th percentile after smoothing your observed data using a gamma kernel. So with that, let's get right into it. Suppose you had the following data: 8, 12, 13, 15, and 15. This could be loss values, this could be claim counts, it doesn't matter. But notice that the data is discrete. We have 5 observations. Your boss comes to you and asks you to calculate a value at risk at the 95th percentile after smoothing your data using a gamma kernel. Your boss also tells you that he wants you to use bandwidth parameter of alpha equal to 1. So given that information, here are your 5 answer choices, and we want to know how to proceed. So before we get into the actual nitty-gritty of the problem, let's make sure we understand first all the terms. So value at risk at the 95th percentile just means that we want to find the value x such that f of x is equal to 0.95. So we want this equation here to be true, and f of x is just equal to your cumulative density function. Okay, so the next interesting term is a kernel. A kernel is just a smoothing function, and instead of having 5 discrete points, we're going to smooth over each of those 5 points, and then we're going to apply an appropriate weighting function to take them all into account. So one way to think of this is, instead of 5 discrete individual points, we have 5 random variables, x1 through x5, that can take on a variety of distributions. And these random variables are distributed via their kernels. You can think, so sometimes I'm going to say they're going to be distributed via their density, sometimes via their kernels, but in this case it's the same thing. And moreover, for each of these kernels, they're going to have the gamma kind of parametrization, but they're all going to be slightly different. Specifically, the mean of each kernel is going to be equal to the observation. So for instance, if we look at the first value, 8, we would expect the mean of the first kernel to also be 8. So mathematically speaking, if x1 corresponds to the random variable, we would expect the integral of x times k y1x to be equal to y1. So notice the kernel here is dependent upon y1, and notice that the mean, the expected value of x1, is equal to y1. Similarly, for the expected value of x2, you would have that equal to y2. And finally, just in case you don't remember, here's the density of the gamma distribution. We're parameterizing it in terms of alpha and theta. And I did some simplification by canceling out the x over here in the numerator and the x over here in the denominator to get x alpha minus 1 here. And I also brought this theta into the denominator here. So that is pretty much the setup of the problem. We have all the terms now, and we can proceed to look into how we actually go about solving it. Now that we've gone ahead and explained every term in the problem, we can now proceed to figure out how we're actually going to tackle it. So let's outline the steps that we're going to do. First, we're going to have to calculate the kernel for each of our observations. So for example, remember that our first observation, y1, is equal to 8. That means we're going to have to calculate k8 of x. Our next observation, y2, is equal to 12. That means we're going to have to calculate k12 of x, and so forth and so on. Once we have all these kernels, we'll then calculate our probability density function here by weighting each of these kernels by the number of times each observation occurs in the data. So for instance, py1 is equal to p8, which is equal to just 1 over 5, because observation 8 occurs only once in the data. In fact, all the observations will be equal to just 1/5, the probability of each observation, I should say, except the last one, because p15, because 15 occurs twice in the data, you're going to get 2 over 5. So once we have that, we're going to integrate out little f of x to get big F of x. So capital F hat x will be equal to the integral 0 to x of little f of t hat x. Notice that the change of variable here, I'm gonna I reparameterized in terms of t to keep mathematical rigor. And then finally, we're gonna solve up here which value of x will give us 0.95. So those are the steps we're going to do to solve this problem. And with that, let's get going. We're now going to look at how we can calculate the kernel for each of our observations. Each kernel will be denoted by kyx, as I show here. Notice that we need to specify what observation we're talking about, what observation y, in order to write out the kernel. So that's because the mean needs to be equal to the observation, as we talked about earlier. Recall that in our case, we're dealing with gamma kernels, and that if you use the standard alpha theta parameterization that you see in the formula sheet, the mean of such a distribution is simply equal to alpha theta. Using information in this problem that alpha is equal to 1, we know that the mean then is just equal to theta, because we get alpha times theta is equal to 1 times theta, which is equal to theta. Furthermore, we know from the properties of kernels that the mean needs to equal to the actual observation in the data that we have. And from what we just looked at here, in our case, the mean is equal to theta. Then, if we combine both these statements together, we get that theta is equal to y. So plugging both of these values of alpha and theta into our density, we see that this part right here simplifies to an exponential distribution with mean y. Observe that gamma alpha is just equal to alpha minus 1 factorial in the case that alpha is an integer. And in our case, that's equal to 1 minus 1 factorial, which is equal to 0 factorial, which is equal to 1. So in our case, the gamma kernel is just an exponential distribution with the mean centered at the observation. And here, so given that we have observations 8, 12, 13, and 15, we just plug these in directly into the formula to get the following kernels. We can now use these kernels to calculate the probability density function as we show in the next step. In this step, we look how to calculate our probability density function using a weighted linear combination of the kernels. So our probability density function is denoted little f hat x. And what we're going to do is we're going to multiply each kernel here by the probability of that observation occurring. So for each kernel is centered at some mean, we're going to find the probability of that mean occurring from our discrete data and multiply them together. This is actually easy to see when you write it all out. All you have to do is calculate probability of 8 occurring times the kernel at 8, plus the probability of 12 occurring times the kernel of 12, all the way out to the probability of 15 occurring times the kernel of 15. The probability of yj is really easy. It's just the is equal to the number of times yj occurs divided by the number of observations. So in our case, the probability of 8 is just equal to 1/5 because there are 5 total observations and 8 occurs once. In fact, probability of 8, probability of 12, and the probability of 13 are all 1/5. The only one that's different is the probability of 15, which is equal to 2/5 because 15 occurs twice in our data. And then we just write it all out in this final line right here, which shows that our probability density function is just a weighted average of exponentials. Now that we have our probability density function, we proceed to integrate that out to get our cumulative density function, capital F hat x over here. So here is little f hat x, this part. We did this in the part just before this. This is little hat fx. We're going to integrate that out with respect to dt from 0 all the way to x. And what we're going to find is this is just we're integrating out a bunch of weighted exponentials. So this should be pretty straightforward. We solved for this long part here in the step before. We're just integrating it out. So remember that if you have the integral of a bunch of sums, under almost all the conditions you're ever going to find on an actuarial exam, you can integrate out each part of the sum individually. So this big integral in this line just means integrate out this part, then integrate out this part, then integrate out this part, then integrate out this part. I factor out a 1/5 to make things easier, and then this just goes from the PDF of an exponential distribution to the CDF of an exponential distribution. You can look this up right in the exam 4C tables, or if you want for practice, you can actually see that the integral, for example, from 0 to x of e to the negative t divided by 8 over 8 will give you 1 minus e to the negative x over 8, so forth and so on. 1 minus e to the negative x over 8. And you can do that for the rest. The only thing you got to be careful for is this extra 2. That's because the observation 15 occurs twice. Always be careful of things like this in the exam. They love to trip you up on stuff like this. So be careful with your constants. But when all is said and done, maybe I'll put this in blue right here. What you're going to get is your cumulative density function is just equal to this expression over here. And from here, we're pretty much done with the problem. We just got to do some last-minute calculations. In this final step of the problem, we want to find the value of x such that when you plug it in into f hat x, you get 0.95. Recall from step 3 that this was our expression for the cumulative density function. We got this by integrating out the probability density function. So this is f hat of x. And we want to find the x such that when you plug that value into this expression, you get 0.95. This is pretty difficult to do without a computer. You'll find that if you choose density at random and try to solve it, a lot of them will be difficult to solve without a computer. I think that's why many of the exam questions either use a uniform or a triangular kernel. However, in this case, we chose our parameters of the gamma distribution carefully so that the CDF was fairly straightforward to obtain. And since we know that there are only 5 possible answer choices, we can try each one of those answer choices and see which one works. And what you'll find is f hat of 38.5 gives you the correct answer that we're looking for. It's just about 0.95. So to solve the problem, you know that the value at risk at the 95th percentile of x is equal to 38.5. So that concludes this problem. We hope that you enjoyed watching the video and that it helped you understand kernels. If you want to see a video on something else, please let us know. If you particularly liked or disliked something, please let us know as well. We'll definitely try to include that or not include that in the next video. And if you liked what you saw, please take a look at actempire.com. We have a textbook available. It has tons of extra problems. When you get the textbook, you get a bunch of extra practice exams, you get a bunch of practice quizzes, bonus material, all sorts of stuff that would help you with the exam. Thank you for watching, and best of luck studying.